Okay, good morning, everyone. Hopefully you can hear me. Just as a sort of logistical description here, we're going to use the chat window. If you have questions, comments, you want to capture our attention for a moment, feel free to chat at us in the chat window from GoToMeeting. My name is Jason Marino. I'm the Chief Consulting Engineer here at Mallett Technology. We're happy all of you could join us. We're going to present 5 topics today. Before we dive in, a very quick introduction to Mallett itself, followed by our structural dynamics discussion, which will be presented by Steve Rugg, one of our consulting engineers. Then Dan Kramer will talk a little bit about LS-Dyna custom materials, followed by a discussion from Mike Owen covering advanced mesh adaptation in CFX. And I'll give a short overview of explicit dynamics. And we've got a treat. We've got a virtual reality discussion with our partners from IQ3, and we'll wrap up with questions and answers. But as I mentioned, feel free to chat at us at any time. Though we may not stop to address the question immediately, we certainly will address the questions, and we hope to have a dynamic discussion. So please feel free. The mission statement of Mallett Technology. We've got a long history since the 70s that's been built around engineering, world-class engineering software tools. And our goal is always to help our customers produce reliable and cost-effective products. So it's our knowledge and experience with these tools and a solid foundation of engineering knowledge as well that we bring to bear to assist our customers with their product development. Okay, so this is a picture of us down here in Research Triangle Park. That's a beautiful picture of our building in spring. Right now, the entire thing's covered in snow. We got 6 inches of snow last night, but we've managed to make it in. We're glad to be here to talk with you guys today. But we've also got offices in Washington, D.C. and Sunnyvale, California. We are a consulting team, but we also support and sell ANSYS software. We've got a lot of different resources at our disposal. Cluster computing, cloud-based computing, and of course the entire suite of ANSYS products. Mallett has a broad customer base. Again, we've been around for 40 years, so we've been dealing with all different industries, ranging from energy to medical to consumer products. You're going to see a little bit of flavor from each of these in the different discussions that we go over today. So with no further ado, I think we'll dive into our first technical topic. Steve, you ready?
Yep. Okay, so while Jason's pulling this up, I'm going to be talking pretty briefly about some structural dynamics. It's an incredibly broad topic, so it's going to be very surface level, but my hope and goal is to at least give a introduction to the topic and a kind of general understanding of what occurs. So specifically, I'm going to be focusing on the modal analysis, random vibration, and shock analyses, and how they kind of interwork together and the benefits you see when simulating those before testing. So you can go to the next slide. So background to this, in pretty much, I'm not going to say all, but many industries require testing to random vibe levels and shock levels to qualify a system that it's robust enough to handle its operational life. Now, the caveat to this is, nowadays, especially when we have simulation, what we end up doing is simulating the shock and random vibration events prior to testing, because that allows us to do 2 things. One, identify any areas that are of concern or that show failure. And then 2 is to redesign it, and so you can walk into testing with a much higher probability of passing without issue. So the 3 analyses from a simulation perspective that are required to do this are the modal, the random vibration, and shock. The one thing I will say is here at Mallett, we do have an extensive amount of experience, one, both simulating these events, but then also supporting our customers during the actual events themselves, whether it's instrumenting them so we can do correlation later, or just witnessing them, or reviewing the test to make sure it corresponds well with the analysis setup. Okay, so before I go into the details of each analysis, I just wanted to cover very briefly a couple key terms that you need to understand to really grasp some of these types of analysis. So the first is resonant frequency or natural frequency. So this term is essentially the frequency at which a given system naturally vibrates. So any system, no matter how complicated or non-complicated, vibrates at a specific frequency when excited, and it desires to. All right, so a couple kind of obvious examples of that would be a tuning fork, right? If you hit a tuning fork, it's always going to vibrate at a tone, right, that it's been manufactured to vibrate at. Bells, different sized bells will vibrate differently, sound differently. If you look at the video on the right, a bridge may have its own natural frequency. So typically, from a design for robustness perspective, usually we want to avoid having a natural frequency in a range that we expect to be excited during operation. Because we can see, especially with the bridge video, when you're at a natural frequency, you can go to the next slide. What happens is, if you're at the natural frequency and you're exciting it, you see a large amplification. So essentially, if I'm exciting a system with little force, but it's at the right frequency, I can see a huge amplification and potentially could cause failure. So stepping slightly back, so what dictates a system's natural frequency? There's really two components. There's the stiffness of the structure and the mass of the structure, right? So if I'm looking at my design and I'm finding that my natural frequencies are too low, I really have two options. One, I can find ways to stiffen it, or I can find ways to reduce mass, and that will increase the natural frequency. Okay, so the next term I want to touch on is random vibration. It is what it sounds, right? So random vibration is essentially vibration that occurs at a range of frequencies, and the amplitude at each frequency varies over time, right? So it's completely random. It's hard to characterize. But what you can find is, if you look at the vibration over a range of time and look at a specific frequency over that range of time, the average value is fairly steady. So what this allows for is a statistical characterization of the random vibration. So if you look in the bottom left picture, you can see we can characterize this using a Gaussian distribution, right, where essentially we look at the amplitude for 1 sigma of the vibration, so 69% of the vibration, and then 2 sigma and 3 sigma, which the general assumption with random vibration from a quality assessment perspective is that 3 sigma should capture pretty much all the behavior, right? It's 99.7% of what will occur over time, and so it's good enough. But essentially what we can do then is, once we understand that it's statistical distribution, we take that distribution and we can apply it to our systems once we understand the operational environments, right? So for instance, this figure on the right, that's a random vibration spectrum that was developed for train cars, right? So testing was done, data was collected, the statistics were used to develop the spectrum, and that's what we use in our simulations. And notice this is also what's used in the test, the actual physical test of the device. Okay, and the final one, in shock I'm going to touch on the least, but the final topic I want to touch on is shock. So what is a shock? So essentially shock is a very short duration event of high intensity. And really the duration and the amplitude of the event determine the total energy of the shock. So there's a very large difference between a shock that's, let's say, 30 milliseconds at 5 Gs and simulating a 5G event over forever, or over 5 seconds. There's a very large difference in the energy. And the second thing I want to note on shock is that shock pulses excite a range of frequencies. So if you think about a tuning fork, when you hit that against something, it's not exciting just the frequency the tuning fork vibrates at. It excites a range of frequencies, and the natural frequency of the tuning fork picks up that input and then amplifies it, and so that's what it vibrates at. Okay, so back to really the analysis then. So from the random vibe and shock perspective, there's really two branches of the analysis. The first is the transient shock analysis, and that leads directly from the simulation setup. You can just walk directly into it. The second is the random vibration, which requires a modal analysis prior to running it. And I'll discuss why in a couple slides. So modal analysis, what is the purpose of this? So modal analysis essentially allows for the calculation of a system's, a few different variables, system's natural frequency, the associated deformed shape of that natural frequency, or at that natural frequency, and the participation factor in each direction of that shape. So if you look at the figures on the bottom left, 3 out of 4, so mode 1, 3, and 4 are all vibrating in the same direction. They're all vibrating vertically, whereas mode 2 is vibrating in the transverse direction, right? So the participation factor would essentially say, if I have excitation vertically, modes 1, 3, and 4 are going to contribute, and 2 is not really going to have any effect. If I have vibration in the transverse direction, 2 is going to have a large effect, where 1, 3, and 4 won't. So then that leads directly into the random vibration analysis. So essentially, there's a mathematical technique called modal superposition that allows you to take the mode shapes that were calculated in the modal analysis and combine them in the random vibration analysis to end up at the final statistical stress distribution for the body. So I kind of show, I'm not going to go into detail in the math, but in the slide below, I kind of show you have three values coming in that we just discussed from the modal, which is the natural frequency, the mode shape, the participation factor. And then using that in the known spectrum, you can calculate the spectrum value, which leads into a mode coefficient, which is essentially saying how much should I amplify my mode shape by to then apply with the other mode shapes that are generated from the other modes, right? So it's a pretty straightforward process, but the modal analysis goes through that because of really the final input from the random vibration analysis is the spectrum. Okay, and so what are the applications? So modal analysis, the largest benefit of doing modal analysis is that it gives you preliminary design assessment, right? While you may not be able to assess stress levels during the modal analysis, what you can look at is the natural frequency of the system, right? So typically for instance, for our customers who work in the train industry, whenever we do a modal analysis on train car components, the desire is to always have all their natural frequencies be above 30 hertz. And the reason is that we know at 20 hertz, the vibration from the train starts to cut off pretty drastically. So if it's at 30 hertz, those frequencies aren't going to be excited, or at least not greatly. So at least it's a preliminary design assessment tool. And then random vibration is pretty strictly focused on fatigue assessments, right? So this could be fatigue of the welds, fatigue of the bolts, or fatigue of the base metals. But it just gives you insight into how it will fail over time and how long that time might take, right? And so typically when we're simulating random vibration, we're looking at random vibration under test conditions. Test conditions are usually fairly intense because they're meant to simulate 20 years of life over, let's say, a 5-hour period. But very similarly, if we were to simulate the true operational vibration, we could look at 20 years of life directly. Okay, so this is the last topic before anyone has any questions. The transient shock analysis, I just want to touch on this. The key I want to point out here is, especially here at Mallett, we're very large proponents of running true transient shock analyses. What this means is that we simulate everything we simulate essentially time, right? We take a period of time, we simulate exactly what would occur in the actual test scenario, right? So we'll start off, get the solution to steady state, and they'll have a shock event that occurs over the exact amount of time the true shock event would, and at each time point through that event, we'll be able to extract stresses and strains and any other data you might be interested in. So the true benefit of that is it's incredibly accurate, right? In the past, especially when computing power wasn't as good, they still exist today, which is why I want to touch on it. But there was this idea of equivalent static analyses. So essentially, if we do some amount of math, we can simulate a shock event via static analysis. The downfall of that, and we've seen this firsthand, is that there's often some accuracy and applicability loss. So we've seen many times, a few times where an equivalent static analysis simulated a shock, results showed it being okay. Then they went to test and the device failed, right? Whereas when simulated with a transient shock analysis, the area that failed was found and correlated, and it gave you a true picture into what was occurring. So this is it's a much more straightforward process than, let's say, the random vibration, because it's a direct representation of what's occurring in reality. So I believe that's the last slide. So with regards to structural dynamics, are there any questions? Feel free to.
Question reads, how do we understand the stress in modal analysis comparing to static analysis in terms of time or probability?
Okay, so one key thing, in modal analysis, you can't extract stress or strain, right? It's strictly a picture of how the body's going to deform. Where the stress comes into play is a random vibration analysis.
Right.
So in terms of time or probability, what we typically look at for random vibration analysis is the first thing we're looking at is it, especially if we're talking about metal, are the stresses below the fatigue limit, right? If they're below the fatigue limit, we're okay everywhere, no issues. If we find that the stress is going above the fatigue limit, what we can do is, using the knowledge that, let's say, we have different ranges of stress, so we have the 1 sigma, 2 sigma, and 3 sigma stress values. We know those are going to occur for a certain portion of the time. So we can essentially, there's a rule out there called the Miner's rule, where you can look at, if I have this stress occurring at a specific frequency, right? A general assumption, let's say in the train car industry, would be 20 hertz. If this stress is vibrating at 20 hertz, we know that that's 20 times a second. How many seconds is this test running? We can make an assessment of how long can it withstand this vibration that's above the fatigue limit, or this stress that's above the fatigue limit. Comparing this to static analysis, I'm not fully understanding the question. Anyone?
Well, one thing that I would add, I suppose, would be to say that modal analysis, as Steve mentioned, gives us a lot of great insight as to how a structure could potentially respond to an input. But to get a deterministic result, be it a displacement or a stress, we need to characterize the input, the excitation, the load. So you first do modal to see what might happen at any given frequency, but you need to know the mode.
Yeah, I would
go ahead.
add that the modes and the mode shapes, the frequencies and the shapes are, you can think of them more as a property of the system rather than the actual stress or strain that it feels.
Right. So once we know the excitation, then we know what coefficient, what multiplying factor to apply to each mode, based on, if the excitation is right on a mode frequency, that mode's going to light up and you're going to see big stress. But you need both. So I don't know if that helps. And static alone will, as Steve said, that's a big downfall for static analysis, is it doesn't capture the amplification, the true dynamic nature, as Dan said, of the system may be lost if you opt for static only.
Right. The reason that there's there's no stress associated with the modal analysis itself, as the modes are sort of an intrinsic property of the system, right? A guitar string has an intrinsic frequency that it will vibrate at, but until you actually excite it, it doesn't vibrate. So there's no way to say from a mode itself what any particular stress or strain might be. It's the interaction between the load and the modes that result in stresses.
Did you pluck it hard or not? Yeah. Okay, any other questions for Steve? Okay, we'll move on then. Next up is Dan?
I think so.
All right.
All right, so I'll be talking about LS-Dyna custom materials, and I suppose a little bit about that is going to be whether or not you might want to go down the route of making custom materials. It's kind of an advanced topic for LS-Dyna, but it's definitely a valuable one, and I hope you get something out of it. So, so first, you know, why even use LS-Dyna in the first place, and ANSYS LS-Dyna. So LS-Dyna is really good at explicit dynamics. It has a lot of options, a lot of materials, a lot of contact algorithms. You can tell all the parts of your system to act in different ways, and it gives you a lot of different, a good deal of control over what exactly happens within the simulation. And ANSYS LS-Dyna is a really great way to access the solver. You can do a lot of things that LS-Dyna can't do by itself. Really good at making geometry, meshing, and you can link it to other types of ANSYS or analyses that are within ANSYS. And almost all of the options that you can get in the LS-Dyna solver are available to you through this ANSYS LS-Dyna. And those that aren't really available are pretty few, but you can add them later after making your input file via ANSYS LS-Dyna. So now that you've chosen to use ANSYS LS-Dyna, why would you have a custom material? So LS-Dyna has a lot of materials, over 250 materials. It surprised me when after using it for so long, seeing that number, it's a lot of materials. So it's pretty likely that you'll be able to find the right material for the job without using a customer user material. But you may need to simulate a material where material laws may exist in LS-Dyna already, but there's just a little something that would, for your application, that you need to improve the accuracy or to make the behavior of the material exactly the way that you observe it to be. So sometimes the material laws are restricted to be linear in some sense, when a nonlinear curve might be better. You might see your material exhibit some things that happen in two separate materials in LS-Dyna, and you might want to combine them into one effect. And sometimes it's possible that you might not be that the material built into LS-Dyna doesn't have enough loading history taken into account, and to accurately predict certain values, stress, temperature, whatever. And sometimes your material might just be strange, and there's not really a material law that exists in LS-Dyna, but that probably won't be the case. And I'll say a little something. You know, LS-Dyna in its inception was kind of geared towards the auto industry. So some materials, I know it's expanded a lot since then, but some materials that might be a little out there and weren't necessarily relevant to the auto industry or auto industry applications might not have all the options that you need, and you would have to come to this custom material. So there's a lot of different ways to customize your LS-Dyna materials and otherwise. You can have different mechanical laws, different thermal laws, how they conduct heat, stores heat, different damage models for fatigue and fracture and all that. And different airbag sensors, going back to the auto industry thing, and different ways to define your contact. Although it has all these options, some of what I'm going to be saying today is going to be more applicable to the mechanical materials side of things as opposed to the rest of them, but most of it should apply to all of these topics. So before you get started, what you really need is to know the material law that you want to implement inside and out. You need to know some solid mechanics. You might have to go back and refresh yourself. I know I did when I had to make a custom material recently. You need to know some Fortran, and you need to be comfortable using the command line, either in Windows or Linux, whichever one you intend to run LS-Dyna in. And unfortunately, you're going to need an Intel Fortran compiler license, which is about $850. You know, just a little pitch for Mallett. If you want us to create a custom material for you, we have an Intel Fortran compiler license, and we would be happy to use ours to make one. And also, if you want to run in parallel, you need the appropriate, it's called MPI compiler files, and that just tells how the different threads, computing threads, can talk to each other, and that's not necessarily built into LS-Dyna, and you need it separately. And also, you need to get the appropriate files from LSTC to compile your custom code. So now that you have all those things, the first thing you need to do is to design your code. And for your mechanical material, you need to be able to take your displacement inputs and transform them into your stress outputs. For those that are deeply in tune with the solid mechanics, you need to be able to take either log strain increments or your deformation gradient and output a true stress or Cauchy tensor. Then, now that you have all your code designed, you have your pseudocode that you want to write in there, you need to edit the Fortran subroutine, and it comes right with those LSTC files that you downloaded from them. So that specific file for your mechanical materials, and you're able to use up to 10 different material laws. They have 10 slots for that. So you can have a wide range of custom materials in your simulation, then compile the code. And lastly, you need to run LS-Dyna. And although in ANSYS, there is a built-in way to run LS-Dyna, since you're compiling a custom material, you'll need to be able to use the command line to run that custom executable. ANSYS doesn't know how to it doesn't know how to exactly find that without you helping it out. And so the rest of this talk will be mostly about these tips when you're doing this. It can be kind of tricky. There are a lot of stumbling blocks. So the first thing that you need to do is really make sure that you need a custom material. Like I said before, there's a lot of materials, and you're probably going to be able to find one that already exists. The second step is you really need to do the research on how you're, like if you just find a material in the field, do your research on how the material responds in different ways. You need to be able to know exactly mathematically how you want your material to respond in different ways, and what other material laws are out there, and what you can draw on and edit for your own purposes. And third, we do this all the time, and people who write code, they do this. You may want to test a very simple case first. You want to output all the steps along the way to make sure everything's going as you expect it to, and you want to test simpler cases when you can that can be compared directly against the LS-Dyna built-in materials, and make sure everything is running exactly as you intended to. And the last thing here is it's not the best feature of LS-Dyna, but if you have multiple materials and you want to use the same material law, you have to put them in separate user match subroutines. So if you have there's 10 available, you can't have the same input for you can't have different parts in your simulation use different inputs with the same material law. You have to copy it over, which is a little frustrating, but it's definitely something to keep in mind. And you almost never see a case where you have 10 different custom materials in your simulation anyway, so it's not a limitation. And definitely, if you write your own material, you want to vectorize everything about it. So that means you want to, first of all, it means you want to use the subroutines that reference a bunch of integration points, a bunch of elements within your finite element analysis all at once. So what that does, and this really speeds it up. Personally, it was 30% faster for the subroutine that I wrote recently. If you move on to the next slide. So this is due in part to reduce computational overhead, and LS-Dyna doesn't have to go back and call your subroutine many, many times. But also, when you vectorize operations, it takes significantly less time because you're just telling the computer to do very few or just one instruction when you multiply one vector to another, as opposed to a number of instructions equal to the length of the vector is shown in there. And that works for all kinds of things, not just multiplication, and really improves the speed of your custom material. The last thing is to be very aware of the stability of your material law. That's something that I have personally run into. So you need to be aware of the internal stability of your subroutine and how your subroutine, your custom material, interacts with the whole LS-Dyna solver. So internally, if you have a nonlinear input or relationship, an inflection point in your material law, that could pose an issue and should be watched out for. And also, if you're looping within your code, you want to make sure that things don't blow up and then have a chance to exit the loop, and so on and so forth. And as to how it interacts with the LS-Dyna solver. Next slide, please. When you have a custom material, you give you have to tell LS-Dyna a stiffness, and the stability of the solver is dictated by, in part, by the stiffness of your materials. So, unfortunately, for a user material, you can only put in a single static value. LS-Dyna is smart enough for some built-in materials. It changes the stiffness that it tells the solver as the stiffness of the material may change, but you only get a single value. This stiffness, it dictates the magnitude of the contact forces. A stiffer material generates higher contact forces when it bumps into something else, and then also dictates the time step of the simulation. So if you can imagine a stiffer material, it'll vibrate faster, and in order to transmit that information between one element to another, your time step will need to be smaller for stiffer materials. And so to be safe, if you have a material that can change stiffness, you want to set this value to be the maximum stiffness possible in your material for the best stability. And if you want to play with fire and increase the speed of your simulation, you can lower the stiffness that you input, but you should be very careful and make sure that everything is running just the way you think it is. So, you know, there's LS-Dyna and there's ANSYS. ANSYS offers user materials. And the first thing to keep in mind is that LS-Dyna is an explicit solver and ANSYS is an implicit solver. And they're both good at different things. LS-Dyna, being an implicit solver, is really good at these shock events and drop tests and unpredictable contact between many bodies. ANSYS, I guess I'm referring to mostly ANSYS implicit, ANSYS mechanical, is really well suited to longer duration events and static or equilibrium loading. And although, you know, neither of these is necessarily restricted to each of those things, but that's the thing to keep in mind when you're choosing between LS-Dyna and ANSYS. And also, another thing to keep in mind is that LS-Dyna is a little more difficult to create a custom material for than ANSYS. So the compiling action in itself, all the overhead you have to do for that is, ANSYS is nice and takes care of a lot of that for you. You don't have to buy a Fortran compiler. You don't need to assemble all the files in the same way. You just open your ANSYS user material file, you edit it, and you double-click an executable, and it's all done. Unfortunately, you still have to write your code in Fortran 77. And here are some good resources. If you decide that you want to write your own custom material, the LS-Dyna user manual, the ANSYS theory manual, there's where you can get all your object files. And that last bullet point is a website that was a good review personally for solid mechanics for me to write my custom material.
It's much easier just to have Dan do it for you, though.
Any questions for Dan regarding LS-Dyna custom materials? Okay, I think we'll move on to Mike. This looks right, Mike?
Yep. All right, everybody. Thank you very much. My name is Michael Owen. I'm a PhD in physics. I'm a principal consulting engineer here at Mallett Technology. I've been with the company about 10 years, and I've probably worked on 100 different projects in every industry. So today, I'm also the fluids guy, if that is not obvious. I'm going to talk about adaptive meshing techniques in CFX. So first of all, why adaptive meshing? Adaptive meshing is often overlooked by people. First, when we say adaptive meshing, what we mean is that the initial mesh that we create does not stay static. The solver is actually going to refine that mesh during solution. So why do we want to use adaptive meshing? Static meshing often involves some compromises, such as over-refinement in some regions, and we're going to have wasted elements and increased run times associated with that. Whereas we might have under-refinement in some regions, and that's going to reduce the accuracy of our results. And to mitigate that with a static mesh often entails a lot of costly engineering time to build a more complicated static mesh. We might use manual geometric slicing or blocking, many mesh controls, a lot of trial and error to get just the perfect static mesh for our problem. And static meshing also typically requires a costly mesh convergence study that results in a lot of over-resolution throughout the domain. It takes a lot of time. So adaptive meshing, next slide, begins with a simple, quick-to-generate coarse mesh, so it doesn't require a lot of engineering time up front, and it adaptively refines that mesh in regions of steep solution gradients. So the elements are spent exactly where they're needed to resolve the solution, and it results in more efficient meshes, increased accuracy, decreased engineering time. It's all around a sort of win-win-win-win-win, but it's very often overlooked. Next slide. So here's an example, a pinhole leak problem. I solved this in 2D. So there's a 4 millimeter diameter hole through a 1 millimeter thick sheet. I have 2 psi gauge pressure on the inside, that's the left, and 0 psi atmospheric on the right. So the question is, what is the rate at which air leaks to within 1%? And if you look at the, I solved this with a static mesh, and I just refined and refined and refined. So my original mesh spacing was 1 millimeter, and I went all the way down to 7.8 microns. And you can see that the number of elements goes from a very small 200 elements up to 3.3 million elements. And this is in 2D, remember. And if you want an answer within 1%, you'll notice you have to go all the way down to 3.3 million elements to get an error of less than 1%. This is with a static mesh. Next slide. So this is what adaptive meshing gives us. So we start with some reasonably coarse mesh, and we adaptively refine the mesh where there are gradients of pressure, temperature, velocity, etc., turbulence kinetic energy in this particular case, turbulent eddy frequency, and we get an extremely accurate result with 63,000 elements instead of 3.3 million. So adaptive meshing can be an extremely powerful tool. Next slide. So it has some limitations, though. First of all, inflated prismatic layers, which is what you get when you inflate a tetrahedral mesh, cannot be refined normal to the wall. That means they won't be, those prisms will not be refined through their thickness. That means that mesh adaptation cannot improve Y plus for inflated prismatic layers. Mesh adaptation is not supported for problems with domain interfaces, porous domains, external solver coupling, transient models, mesh motion, radiative tracking, or particle transport. That sounds like a lot of limitations. The most important one, the most commonly run into one, is that you can't use mesh adaptation when you have domain interfaces. So let's talk about domain interfaces. Why would you use domain interfaces? First of all, they're the CFX equivalent of contacts. They connect different domains or even distinct internal regions in the same domain, and they can be used for a lot of regions. They connect fluid domains to solid domains for conjugate heat transfer. They connect fluid domains to porous domains. They can connect regions with different frames of reference, for example, turbo machinery simulations. Periodic boundaries, you can use them to specify pressure drops like screens or fans, thin surface physics. Most commonly, they're just used to connect fluid domains with dissimilar or what we call non-conformal meshes. So those meshes might be generated by different engineers. They might be generated in different meshing tools, or perhaps they're just, you slice the domain to make it easy to generate the meshes in the two different regions, and you need to connect them back together. So use of domain interfaces is extremely common. You will hear some people talk down about domain interfaces, but as long as they're properly used, they do not compromise your convergence, your runtime, or the accuracy of your solution. I have a little tip for you there. If you're using domain interfaces and you see convergence problems, it's almost certainly that either you're not adequately resolving the solution gradients on either side of the mesh, or that you have mismatched inflation layers. If you have mismatched inflation layers on either side of the domain interface, you'll get convergence problems. Next slide. So mesh adaptation with domain interfaces. This is not directly supported. So I'm going to give you a workaround. This works great. So first, build the model with domain interfaces exactly the way you would if mesh adaptation were supported. So you've got a coarse mesh, easily generated. Remember, Y plus cannot be improved by mesh adaptation for tetrahedral meshes. So be aware of that. Prismatic layers, by the way, can be adapted tangential to the surface, but if there's underlying curvature that you're in the surface geometry that is not captured by the original mesh, the mesh adaptation cannot recover that lost curvature. Next slide. So this is an example that I created. We have two regions here. There's this green region, which is a pipe that has a square slot cut into it, and that is inserted into this box region that has another pipe exiting from it. So these are two non-conformal meshes. The blue mesh is entirely conformal to itself. The green is as well. And they need a domain interface to connect the slot that leads from the pipe. So this is the problem that I want to solve with mesh adaptation, but I need a domain interface to solve it. Next slide. So first, solve the complete course model with the domain interface. Post-process that course model in post and export from each side of the domain interface profile boundary conditions of the appropriate type. Next slide. And that looks like this. We have a geometry, we have a mesh, we have a model with a domain interface. We solved it, we've post-processed it, and we've exported some profile boundary conditions from the two sides of the domain interface. Next slide. Then you want to take that model and duplicate it twice. And in each one of those, you're going to delete one of the conformal meshes, leaving only the other one. And you're going to initialize profile data and use the profile boundary condition data that you exported from the full course model and create, instead of one side of a domain interface, you're just going to create a boundary condition and apply that profile data to it. And you're going to resolve that model adaptively. And next slide. That looks like this. So each one of these systems, D and F, I don't know what happened to E, but in each one of these systems, D and F, you have adaptively solved one region of the domain using the boundary conditions that came from the full domain. Next slide. Then you're going to open a fresh instance of CFX Pre, no models or meshes, and you're going to just import the meshes from the two results files that you created. Those will contain the adaptations to the mesh in them. And then finally, you're going to import the CCL from the original course model. That contains the domain interface and all the original boundary conditions. Resolve that full model with the adaptive meshes and post-process on it to make sure that the adapted meshes accurately resolve the full final solution. Next slide. So here's the final example. So that's what happened to E. Actually, I had erased the connection to E in the last slide. But that model is the full model with both adapted meshes and the domain interface. And you can see in the full final model that we have exactly what we were after, the full model adapted with domain interfaces. So that's a neat little technique, and it will allow you to work around this limitation. Next slide. There are other limitations that you can overcome for mesh adaptation using the same sort of idea. So mesh adaptation is not supported for cases with radiative transfer. Okay, fine. Adaptively solve the problem first without radiative transfer, then import the adaptive mesh and solve it with radiative transfer. And as always, presumably you're solving with radiative transfer because it's important. You need to make sure that the presence of radiative transfer has not changed the solution so much that the adaptive mesh is no longer valid. So that's always an important step to check that. You can use this technique for conjugate heat transfer problems. Conjugate heat transfer problems have solid domains and fluid domains, so you'll always have domain interfaces. You can solve the coarse conjugate heat transfer problem. From post, you can export temperature profile boundary conditions on the fluid side of the fluid-solid domain interfaces, and then adaptively solve the fluid-only mesh with the profile boundary conditions instead of having solid bodies and domain interfaces. Again, recombine the adaptive mesh and the solid meshes resolve the full model and again make sure that the presence of conjugate heat transfer has not invalidated your adapted solution. And you can apply this idea to most of the other limitations of mesh adaptation. Last question. I ran into this very recently on a job that I was doing. Can you adapt an adapted mesh? No, and then yes. So the question is, can you import an adapted mesh and then adapt it again? And the example I came up with recently was I had a free surface mixing case, and trying to adapt on all the variables at the same time resulted in the adaptation for, it was a tracer value occurring in the wrong place. And so instead I wanted to sequentially adapt on volume fraction to find the free surface and velocity to get the flow field correct. And then after that was done, adapt on the value of my tracer that was moving through the fluid domain. That's not directly supported, but there is a workaround. Once you have adapted the mesh the first time, you can import that adapted mesh into finite element modeler, send it downstream to a mechanical model, and then plug it into CFX. That, as far as CFX is concerned, is a completely fresh mesh. It has no knowledge that it has been previously adapted, and you can adapt on it. So if you go to the next slide, you'll see you're looking at the top, the workflow, which is geometry to the original mesh. I initialized it on the coarse mesh and then adapted it. That's system D. Then completely disconnected is system E. I import the adapted mesh, bring it into a mechanical model. What you're looking at down below that is you're actually in mechanical looking at the adapted mesh. And you'll notice there are no mesh controls associated with this. This is an imported mesh that went downstream to CFX, where I adapted it on my acid tracer value. So the point is, mesh adaptation is an extremely useful tool. It's often overlooked. It does have some limitations, but if you're clever, you can get around virtually all of those limitations.
Any questions for Mike regarding CFX mesh adaptation? Again, feel free to chat right in at any time during the presentation, and we'll be sure to catch up and address those.
Yeah, we have, as a reminder, if you came in late, we have everybody muted because we get a lot of echoes and feedback. But if you do have questions, you can enter them in the your chat window, and we'll be able to answer them.
We'll also have a session on the question and answer then.
Mm-hmm. Okay, our last technical topic regarding the finite element solutions is explicit dynamics. After that, we've got one more topic with our IQ3 virtual reality partners. But my name's Jason Marino, again, I'm Chief Consulting Engineer. We'll have a look at explicit dynamics. So Dan talked to you about LS-Dyna and you know, his custom material laws, but he also touched on the difference between LS-Dyna and ANSYS. And we, you know, he took us through this description of Dyna being suitable for impact and short duration kind of events. It's often almost always associated with those types of problems. I just love watching stuff like this. But what can Dyna do? Watch what it can. Dyna could simulate this event verbatim. We've got wrinkling and crumpling of sheet metal. We've got fracture of glass. Just tremendous amounts of nonlinearity from every possible source are going on here. Friction, lots and lots of body-to-body interaction. This is where Dyna excels. It's also used a lot in ballistics, whether they be internal, external ballistics, or even the impact and or detonation of a device. You know, this is where Dyna is typically associated. However, let's not forget, it can do a lot of other things. You know, Dan touched on exotic materials. all these post-buckling. It's used for forming and stamping simulations, you name it. Even in simulations that we might be tempted to use ANSYS, we often make a choice to use Dyna to capture body-to-body contact because the explicit solver just carries significant advantages for stability and ease of use for that kind of problem. So implicit versus explicit. We'll do a little math. I'll try to be quick and just kind of give an overview here. But basically, right, we've got the equation of motion. Everybody knows F equals ma, right? This is mass acceleration. We've got a damping term, and our good old Hooke's law is stiffness or elasticity contribution. Remember, when we're doing a static problem, we ignore these first two terms here, and we just do F equals kx. Obviously, a transient solution is going to take into account inertia. It's got all this stuff going on. Our choice becomes, how do we want to solve this equation? We have to march through time, so we have to employ some form of time integration, and that's where the difference comes in, the ANSYS implicit solver versus the LS-Dyna explicit solver. The big difference here, in the implicit world, we assemble a simultaneous system of equations, and then we iterate that system to a state of equilibrium, versus the explicit method where we never assemble the full global system. We go element by element, degree of freedom by degree of freedom. The equations are uncoupled, and we simply execute sort of a predictive step to say, what is the degree of freedom going to look like in the next time step? So this is another way to look at the same thing I just talked about, right? An implicit solver is going to put, let's say you have 1 million nodes, and each node has 3 degrees of freedom, X, Y, and Z. That would give us 3 million degrees of freedom. This vector is 3 million tall. This matrix is 3 million by 3 million. An implicit solver requires us to assemble that entire matrix, ideally hold it in memory, invert it, and proceed with solution. Once we have our solution of unknowns here, assuming it's a nonlinear problem, we have to plug them back in, recompile, reassemble this full global matrix and solve it again. And keep doing that until equilibrium, until we get the right forces out the other side, right? Looking over here, this is the explicit side. It maybe doesn't appear to be simpler, but the key to keep in mind here, this is time n plus 1. This is the future. On the left-hand side in this, it's kind of backwards. Usually think of that as the right-hand side. But the other side of the equation, n minus 1, n minus 1. So these are past time points. Simply plugging in, we do have to compute element-level stiffness matrices. There's no way around that. But this is per degree of freedom. 1 by 1, we can make this equation and boop, pop out what it's going to look like at the next time instant. The only requirement we've got here is that the mass and damping matrices are required to be diagonal. But that's not even uncommon on the implicit side. Often, even over here, we see this as diagonal matrix. It doesn't have to be, but damping is often diagonal as well. So that's a requirement for the explicit method. But you can see here that we can march through. Dan talked about vectorized operations. Bang, we can make a time step prediction in the explicit world very quickly and efficiently. But there's a hang up there. We can't march forward in time at an arbitrarily quick pace when we're doing this forward-looking scheme. We have to proceed at a rate that captures the degree of freedom interaction from one to its neighbor, to its neighbor, and to its neighbor. We need to propagate information through the domain. So this is a good example, right? The bottom half of the slinky, he's at equilibrium at the beginning. He's got tension from all the elements above him and gravity pulling down. And that bottom end of the slinky does not become aware that the top end was released for some true duration of time. So if we march through an event like this little by little, and we discretize time sufficiently, we can propagate the information through the domain and capture the true event, right? So that's our limitation. It's often, we hopefully know the CFL limit. It just basically states that we have to take very small time steps, small enough that we don't lose information essentially within a given element or whatever, however fine we discretize this domain as we march through time. All right, so here's just another way to imagine that this is not an explicit dynamic solution, but I like it because it just kind of shows, look, if we got all these slinkies and we grab hold of one, and we just kind of advance through time a little bit, we can watch how that information can move into and through the domain, right? Okay, so one final way to kind of look at what the advantages are for explicit. The nonlinearities, if they're present, especially like Dan was talking about, material nonlinearities, they're going to appear here in this stiffness matrix. They're readily captured during the incremental updates. You might have sub-iterations when you're kind of figuring out where are you exactly on your stress strain curve for a given increment, but you don't have to, as opposed to over here. This stiffness matrix itself depends on the solution. So we have to solve it, plug back in. If there's a lot of nonlinearity going on in here, you can imagine the expense. You've got to go through a Newton's method, some convergence criterion, and so on, and solve this repeatedly. The thing, though, is, so this guy, we said, he's going to require very, very small time steps, you know, down microseconds and lower. But we do lots of them, and they're cheap. Over here, we have no limitation. We can march through time as quickly as we want. It might cost us more equilibrium iterations to march faster. But you can see here, like, if your dominant response is a low frequency with like 1 hertz, you might get away with marching through that at 1/10 of a second, 100 milliseconds. You can have 1 second done in 10 steps versus over here, maybe 1,000,000 steps. So those slower, kind of low frequency type of problems will stay over here on the implicit side. Crash, impact, high nonlinearity, lots of contact. We come over here and take advantage of the explicit solution. So the rest of the presentation is just some examples of the work that we've done here at Mallett using this kind of solver. This is a handheld medical monitor. It's if you were to look at one, you might think it's like a mobile phone. It looks like a smartphone. But this is just a typical drop and impact analysis. We pick up all kinds of stuff. We actually were looking at BGA failures, solder joint failures on the circuit board in this device, and helped them to make some geometry changes to reduce the stresses into the core of the device. It also has a glass touch screen. We're familiar with and capable of predicting glass failure and that kind of thing. This is a mining equipment. So they don't take a canary down in the mine anymore. They take one of these bad boys down there, and he can sniff the air and tell them when to get out. It rings a tremendously loud alarm and all this good stuff. But as you might imagine, the environment is very rough and tumble down in the mine. So they beat these things up pretty good, and they want to make sure before they send it out in the field that it can survive the sort of abuse it might see in a mining site. Similarly, we're predicting this is a big battery, a big mass down here. There are circuit boards and other electronics components. I think this is the loudspeaker and the siren and so on. This is a military application. We have a 40-millimeter grenade. Inside the grenade is a glass ampule filled with signature material. This is actually a practice range round. They want this signature material to plume into the air upon impact with the ground, so that the gunner can see, and it's used for target practice basically. But a lot of stuff going on here. We've got ground interaction. We modeled the soil. This was correlated to a particular hard packed clay down in Arkansas, one of the Army ranges down there. We've got this plastic ogive that breaks up the glass inside, and then the splaying out and pluming. Here's the signature material. It's like a dust or powder, but it swirls around while the round is flying, and then at impact, of course, it does its thing. This is a case where we use LS-Dyna because of exotic materials. These are foam stack materials, and then all the delicate interaction and contact, the crazy amounts of different contact interfaces going on in a case like this. And here's another case where you've just got a lot of body-to-body interaction. And it's a nice dynamic event that LS-Dyna handles very, very nicely. So that's it for our explicit dynamics. Are there any questions I can answer? No?
No, just give
Okay.
give people a good time. Maybe
Yeah.
you can also a question related to other presentations.
Yeah, any questions in general for the Mallett staff? Sure.
You can open the.
I'll try. I'm going to try to unmute the mic. If it feeds back, we'll let's see. Okay, with that, Abba, do you want to give an introduction for Michael, or?
No, Michael, you can do it.
Okay. Yeah, you got it.
Oh, you want to set me up?
Yeah. Get you in here. And you're live.
All right, so now we're going to exercise a different part of your brain. Take a look at this picture. It looks a little bit odd. Something's not quite right. You know, that water's sort of just like sitting there. But what if I look at it from a different point of view? See, if I look at it at a different point of view, it's straightforward what it is. It's this young woman who's just leaning up the side of the swimming pool with her back floating in the water. And you see, photographers have understood that this point of view is very important. It changes the way you think of something. You know, you saw that initial picture and it looked a little strange. It didn't seem right. And you look at this one, this is the way we're all used to seeing it. And as I said, photographers understand this point of view, how to change the perspective of a photograph to change the way you see something. And they can do it with just about any media. I mean, you see a lot of these photos these days where people hold up the sun. Here, someone's got the Eiffel Tower between their fingers. With photographs, it's quite easy to change that perspective or point of view. But what about our very complex products? You know, this is an aircraft, and just looking at this, maybe if you design aircraft, you can make sense of all the stuff that's going on in here. But every product that we look at today is more and more complex. There's a lot more things going on, and not everybody has the same understanding as the person who designs the electrical system, the plumbing system, the mechanical system. Everybody has a different view of how that product goes together. And what you find a lot of times is you have the engineering team and the management team, and they don't see eye to eye. And this one, the engineers see this, it's got 4 pipes, where the management says, no, it's only got 3, it's got to be cheap to make, don't worry about it. But the engineer knows it's going to be expensive because there's 4 things they've got to take care of in there. You see, that perspective is critical. And we want to make sure that everybody is always on the same page. I mean, today, we've had some great presentations of some very complex topics. And as engineers, we understand that. I'm a mechanical engineer, so I actually enjoyed the last hour and a half. It was actually really good to get back involved in some of the nitty-gritty. But when you think about it, when you try to explain some of this material to people who maybe don't have that same background, or they come at it from a different approach, it sometimes takes a lot of time to get your point across, to make them understand what you want to change in that product design to make it better. And that's what we're about here. We're going to talk about how to use virtual reality to help get your ideas understood by people who don't necessarily think the same way you do. And it's really important because a lot of cost goes into developing these complex products, and you don't want mistakes to happen. And you want your ideas to be understood so that they can get implemented and make sure that that product gets out on time and it achieves the job it was designed to do. And so let's talk about a company that this has happened to. Boeing 787. I think you'll all remember many years ago, it was headline news. And it was headline news for not a very good reason. There was this picture. This was in Boston Airport, where the fire department had to be called because the plane was smoking really badly. Luckily, there was nobody on the plane. They just deplaned. But the fire department couldn't actually put out the fire for hours. There was other pictures shortly after where you saw the plane being deplaned. It had to make an emergency landing, and everybody had to get off the plane, again, because of smoke on board the plane. Very costly mistake for this company. And it was all related to this lithium-ion battery. It's a big problem for them. You know, they thought it was designed right, but obviously there was something in that design that wasn't quite right. And so they had to go back and redesign that battery. But what really cost this company a lot of money is they kept making these airplanes because they couldn't stop production. And I was actually out at this airfield where they make this airplane. There was so many planes at that airport that they couldn't even land or take off any new airplanes there. They were parked all over the airfield. This cost Boeing billions of dollars, billions and billions of dollars. They had to fix the problem fast. And we showed you this image before. The Boeing engineers knew that they had to communicate with their management very quickly and effectively in order to make sure that they could get their design change across to management and get the buy-in for that design change quickly so it could get implemented. And so at the time, Boeing was implementing a new technology called virtual reality. And so they decided to use virtual reality in this instance to help get their message across of the design fix. Because this design fix, it wasn't just re-engineering that battery. In order to satisfy the authorities that that aircraft would be safe to fly if they did have another battery fire, they had to actually redesign the whole exhaust system. They had to encase the battery and create venting for it. So if the battery did catch on fire, they were able to contain the fire and exhaust all the poisonous gases out of the aircraft without obviously hurting or killing people that are on the airplane or creating a major catastrophe of a plane crash. So Boeing engineers used virtual reality to get their ideas across much more quickly, because this actually required that they redesign part of the back end of that aircraft. And if you look, there's a pipe here. And this pipe went from sort of mid-level in the aircraft, and they had to get it all the way through the fuselage down to exit on the bottom of the aircraft. And so when they designed the aircraft, it wasn't designed for this pipe to be there. So you can imagine what they had to go through in order to fit this pipe in there. And the best way they could explain how they had to make modifications was to use virtual reality to get their point across to management. Obviously, the fix worked. These planes are flying now, and I don't think they've had another fire since. So, you know, it's important that we make sure that we can get our ideas across quickly. And so why does VR work that way? Well, if you look at the research on VR, I'm going to read some of this. You know, understanding scale is notoriously tricky on paper. You know, humans are, after all, we're visual creatures. For example, telling somebody a statistic, a stat, say how many thousands of people are living in a refugee camp, that's one thing. But showing the scale of that camp, if you could draw it out, if you could show them a picture of the thousands of people living in that camp, that gives them a much better understanding of what's really going on. And see, because perspective is powerful, it leads to a better understanding. And moments of revelations tend to stick in the mind of the audience. And that's what VR can do. It gives you a much better perspective. It helps you understand better. And when you understand something better, it sticks in your head longer. And then you can actually explain it to others much easier. And obviously IQ3, we're not the only ones who are talking about VR. There's a lot of people out there talking about VR. And I'm just, you know, Microsoft, they believe that VR should be on everybody's computer monitor going forward. They're thinking of actually replacing computer monitors with VR headsets. And if you look at Forbes, they talk about how 5 industries are already using virtual reality. And I talked about Boeing. So the aerospace industry is a big industry that's implemented VR already. And then even Bloomberg, you know, financial news, they're talking about computing's next big thing. The virtual world may be a reality by 2020. Oculus, the people who have the, you know, the Oculus Rift, it was initially designed for gamers, but they realized the power of this in the industrial application. And they're setting up a way to distribute this tool to industry and make sure it's supported in an industrial way. And Microsoft, of course, the big thing, and this is why we're here today, what they believe the really power of VR is in communication. As I talked about earlier, how do you communicate your ideas? Well, VR gives you that tool to communicate them more effectively. So why is VR special? Remembering things visually and in the context of the space around us just comes more naturally. And this is where VR can shine. VR enriches the layers of vision, space, and user-driven exploration. All these layers help to strengthen the memories and the feelings associated with them. See, VR makes it more real. And when it's more real, you get it better. You immerse yourself in a virtual reality. It's like being with the real products. So, as we mentioned earlier, today's products are quite complex. And what we do today when we're trying to communicate this complexity of what we need to change perhaps of the design because it's not right, we've done some good engineering analysis work, some real good engineering, and we find out, oh, this product's not going to work, we need to change it. How do you communicate that change effectively with a product that's very complex? Well, today, what we tend to do is, what we're kind of doing right now, is we're using WebEx or GoToMeeting, and you'll sit in a room with a bunch of people, and up on a board you might have a TV screen, and on the other screen you have a whiteboard, and you're kind of showing your product in a flat image, in a 2D image. Well, because you're the engineer, you created that material, you get it. And the other engineers like-minded to you will get it. But what about that poor manager in the room who doesn't do this every day? They don't get it as easily, and it takes a lot of time to get it across to them. So you might actually decide, well, we're going to get on a plane and go meet with that manager and see him face-to-face and explain it to him face-to-face. That's quite costly. It takes a lot of your time. You've got to fly to get there. You've got to fly to get back. And now you have all the time sitting with the manager, explaining to them, or with the other engineering teams or production teams. It's very costly. It takes a lot of time. It's not much fun. So what's going on? Well, WebEx, as we know, and GoToMeeting, they're very powerful tools for connecting people. And they're really good for communicating flat imagery. They're not very good for communicating 3D imagery. And that is because you're looking at a flat screen. You don't have perspective and you don't have one-to-one scale. So the question is, what if you could combine the power, the accessibility of teleconferencing with the value and understanding that you get from virtual reality, making a virtual meeting space? Well, if you can do that, then you can more easily get your ideas across to people who aren't even with you, who don't have the product directly in front of them, because they can experience it like it was directly in front of them. So as those news articles said, the future really is about having virtual meetings where you immerse yourself with your products, your understanding of the engineering challenges, your understandings of the engineering results and what it means to changing that product. And so what this is really all about, it's compressing decision time through better collaboration, right? We want to get that answer out there faster and solve the problems faster. So we need to be more effective in the way we collaborate. Let's talk about how a company is implementing that. There's a company called AVL. And they're a global company, and they make automotive test equipment. So they make the machines that they use to test powertrains, full vehicles, cars, trucks, tractors, earth-moving vehicles. And what they do is they develop the machines, but they also then have to integrate them into a facility. And so what they'll do is they'll create these engineering drawings, these CAD drawings with their engineering solutions built into them. And they'll create this based off their understanding. They've been out to look at the facility, they measure it up, and then they come back and they design and engineer their solution to fit into a facility. And invariably what happens is it's never quite right. There's something that got missed, where some pipes, some doorways were, where some existing equipment was, and they missed out on it. So what they've started to do now is they'll go and they'll do a scan, a 3D point cloud scan of the existing facility. And they'll take this 3D point cloud scan and they'll bring it back to their office and they will read it in and combine it with their CAD tool. So here you can see the green is sort of the CAD overlay of the point cloud. And they do this just to validate that the point cloud was correct. But then what they will do is they'll just use that point cloud and insert their new components, the pieces that they're going to change. And they'll work out where they place all those components. And then what they do is they do it in virtual reality. They'll have their engineers, their managers walk through the facility, and then they'll have their customers walk through their own facility with the new equipment in it. And this way, what happens is the customer gets to understand the change that's being promoted by AVL and understand if it's actually going to work for them. Because in the old days, what would happen is they get this all installed, and then the customer would say, this piece of equipment doesn't work for us in this space. And there'd be a huge cost overruns because they'd have to re-engineer, redesign part of the facility. And so today, their customer can actually put a VR headset on and walk around their existing facility with new equipment in it and get an understanding of how the workflow is going to work. And if you talk to the manager at AVL, he says, by using VR, we now can effectively communicate both internally and with our customers in 30 minutes instead of the day-long meetings it used to take, dramatically reducing the time to get to consensus and make the right decisions. Just think, if you could get to a consensus in less than 1/10 of the time, how much time are you going to save working with your managers, your customers, your production teams? So, does anyone have any idea what this is? What this contraption is?
It's a beer pouring machine.
It's a beer pouring machine. It looks a little bit complex. It's probably not too difficult, but I would probably, instead of using this machine, I'd probably just grab that bottle and pour my beer. I've poured a few beers, so I can actually pour them pretty effectively without them spilling all over the place. So maybe a little bit hard to use, not that easy. I was in a Japanese airport, and they have one of these machines. And it's basically an automatic beer pouring machine. You put your glass in there, you push a button, and it tilts the glass, pours the beer, you get a perfect beer every single time. I actually use this machine. Why? Because it's easy to use. And the truth is, all of us, we want things to be easy to use. The easier they are to use, the more likely we are going to be to use them. Today, we all learned some nice tricks of implementing some very complex engineering solutions. Why? To make them easier to implement and easier to use. Now, I encourage you, with those engineering solutions you heard about today, implement them, because it will make your job easier. And when it's easier to do it, you're more likely to use it and then get a better answer to promote to your managers. So this is all about ease of use. And the issue with VR in the past is it's not been that easy to use. You have to have very expensive and complex hardware and very expensive and complex software. So we need to make it much easier to use so that people will actually pick it up and want to use it. And again, this is where IQ3 comes in. We've created a system that's very easy to use. We have a simple server environment. The server environment is the back end. It can take your data and it will process it fully automatically for you. So that's happening in the back end, processing the data to make it so it can be rendered in a virtual world. That happens in the back end. You don't even have to worry about that. It just happens. On the front end, what you use is a very simple device, a computer that can drive a virtual reality headset. It's typically a pretty powerful engineering computer that has a good graphics card in it. It will be strong enough to power virtual reality. That's if you want to do it in virtual reality. It's also possible to collaborate with your colleagues by just using a tablet or a flat screen TV. Yeah, you lose the power of the VR, but at least you can easily now collaborate very effectively with your colleagues. And so ease of use is really important. So what we do is we call this, it's simple drag and drop. You take your data, you drag it and you drop it into the IQ3 software, and then that server in the back end will take care of everything else. And when it's ready to be rendered, it will come up, it'll show up on your screen as a rendered data set. Drag and drop, as simple as it can get. So there's a Japanese auto manufacturer, and unfortunately I can't give you the name, not yet. Soon we'll be able to. But this Japanese auto manufacturer is implementing this easy-to-use virtual reality solution. And why do they want to do this? Well, they have facilities, obviously, in Japan. They're headquartered in Japan. Lots of manufacturing, lots of engineering, lots of product management in Japan. But in North America, they have a design center in California. And in Ohio, they have engineering and development teams as well as manufacturing. And the issue is they're building the same vehicles in all these same places, have engineering teams in all these places, and they have design studios in all these 3 places. And they all need to be on the same page. And what it used to take is these people getting on an airplane and sending 4 or 5 people to have meetings. And these are international travel. So they're losing a day traveling there and a day traveling back, plus the cost of all that travel, the cost of the lost time of the travel. They need to get the people on the same page. So they've implemented a collaborative VR environment. And what I want to say is the engineer, the manager of their IT organization that implemented this, this is what he had to say. We've tried to implement a collaborative VR solution before, but have never succeeded until now. See, with IQ3, it is easy. It's easy to install, easy to implement, easy to use. It just works. They sent a team from the US to Japan, and within a half hour, they had a system set up, and they were collaborating between all 3 regions. That's how easy it is. And that's why they're fully implementing it. They've tried other solutions, but they're very costly, very expensive, and very hard to use. And they haven't been able to get them to work yet. With IQ3, they're able to get it to work instantly. And that's because it's a browser-based technology. So the client-side environment, it works off a simple browser. And you open up your browser, and this is what you would drag and drop your file into, and then it communicates with that server, processes data, and then you're communicating with all your colleagues through this browser environment. You don't need to install special software on your machine. You just use a browser to do it. So, in summary, we had this beer pouring machine, and if it wasn't easy to use, you didn't use it. But when I found one that all I had to do is push a button, I started using it. Any software tool that we use today, any engineering application that we want to implement, it has to be easy to use, otherwise we won't use it. We talked about WebEx and GoToMeeting, and they're really great collaboration tools, but they're not great for collaborating ideas when we're talking about 3-dimensional objects. So you need to have a way to be able to collaborate in 3D, and that's by using VR in an effective collaboration tool. And at the very beginning, I showed you this picture, and it looked a little bit odd. And it really just has to do with our point of view, our perspective. And when you look at it with the right perspective, you get a better understanding. And virtual reality is a way to get that better understanding, get people to understand your ideas so that you can more effectively get your job done, get on with the real work, because people now understand much more quickly. So that's why VR is important. And I know it's the reason we can't demonstrate VR is because you have to put the headset on to really understand it. Doing it over a 2D media like we just did, it doesn't do it justice. So what I would ask, if there's any questions, what do you think about this? I'd also state that if you really want to learn more, bring us in. Give Mallett a call and bring us into your facility, and we can give you an on-site demonstration, and we can even do it with your data if necessary. So thanks for the time, and thanks for my host at Mallett for letting me in.
Yeah, thank you. Good. Thank you.
All right. Okay. I think, yeah, if we have any general questions, anything at all related to anything you've seen or heard today? Otherwise,
5 minutes. Let's wait a few minutes and then see if some people will.
Yeah, remember we have everybody muted, so if you want to ask a question, please use the chat window.
absolutely, yes.
Can you scroll down on the chat window? It looks like it's in the middle. No, in the chat window.
In the chat window.
Oh, shoot. Oh, my goodness. It hadn't been, okay, so we do have one.
Up here, looks like.
Did we get them all? This is the last 2. I'm sorry. Gary, we missed you earlier. It says, is there a material database available to users, and how should we set up the damping factor? So this could have applied to either Steve's talk or mine, any dynamic analysis in general. And I guess I'd begin by saying that ANSYS, with an STR or explicit dynamics license, does come with an extensive material database. It's quite impressive, really. And if nothing else, it at least gives you a good starting point. So, for example, I showed you animations of glass shattering, that ampule inside the 40 millimeter grenade, as well as the glass on something like a smartphone. There are, I think, 3 glass models with failure mechanisms all built in. We have different polymers, many different metals. All that is available. The damping factor is a little more tricky, and there are rules of thumb out there, of course. Generally speaking, we lean toward the conservative side and assign a low degree of damping, say 1%. However, in cases where we know that fluidic damping, basically air interaction, for example, on large sheet metal bodies and so forth, we've raised the damping factor there. But the best way for us to get a firm grasp on the particular damping for a given structure is to instrument the structure with accelerometers or other test-related sort of setups. And once we do that, if we're in the modal environment or even in the transient environment, we can target particular frequencies. For example, if we have a large sheet metal structure where some of the modes involve a lot of just sheet metal motion, is pumping air, and we need a lot of damping for those, say 10% or even more, versus other modes where we have something sitting on a stiff spring, it's not damped much, we can basically do modal damping to address those. And we have rules of thumb and a vast amount of experience to determine an appropriate estimation up front, but for critical applications or high accuracy type of situations, our best friend is test, or even previous programs, something to give us a hint on that.
Universal, unrelated question.
HPC, is it possible to purchase HPC license for a small period of time if the license is not needed for a full year? So Abid, you can handle that.
Yeah, you mean ANSYS, the question, if it's related to ANSYS, so that, yeah, ANSYS, yeah, it's limited, it's possible to do limited license. Clearly.
Yeah, there's leasing options available, and there's also, it's still up and coming, but there are cloud-based elastic licensing and other sort of, we can call them burst licensing, if you will. These types of setups are available, but this is a terrific question, and I think
send an email to Mayton Ozen on this. When you post, put Mayton's email address, Jason, if you don't mind. Put the first slide.
Well, we can just we can put it here, but
yeah, contact Mallett, contact Mayton regarding. Yeah.
Oh, he's got his email here, so we're all good. Thank you, Jason. We're very appreciative. We'll get in touch with you.
Can you scroll up and make sure we didn't miss any other questions?
Yeah.
I think we got one there. So this was, where do you get the input for a transient shock?
So typically it's the relevant standard for, So typically for transient shock, it's a relevant standard for industry, right? So if you're military 810 will have shocks, but shock, I think it's a sawtooth shock for a lot of stuff in 810. Train industry, IEC 61373. It just depends on the relevant standard, and they'll have both the random bias spectrums as well as the shock pulse.
Right. ASTM also has a full suite of different shock spectra related to packaging, you know, like a box falling off the back of a truck, that kind of stuff. Those types of shock pulses have been characterized and standardized. So it really just depends on your industry and what you're after. There's even a military, you can get as far as torpedo impact on submarine hull and all this kind of stuff. These types of things are out there and available. Again, it just depends on where you're coming from.
Yeah, and I would say one more thing would be even earthquake noise on buildings, right? They have both vibration and shock events for earthquakes in the civil codes. So it's really just, people have done the legwork in the past to develop the codes that would accurately represent the events occurring in real life.
But there are the other way to go about it. If you're unsure of exactly what your shock impulse should be, then we simply model the transient event. Say you want a train car coupling event. Two cars are going to bump into one another, right? And we've got a coupler in there. There is a standard out there that tells us what kind of forces we should expect, but if we've got something unique about our coupler or something different about our car or whatever it is, we just model the event. We use LS-Dyna or ANSYS, depending on what, we talked about all these different, advantages and disadvantages, but we just model the impact. And then the shock pulse itself is a result of the calculation.
Could you check if there are more questions?
Yeah, appreciate your patience, guys. We may have missed a couple of questions here till the end, but if there are any others.
Yeah, we apologize. We kept telling you to use the chat window, but the chat window was not scrolling, so we didn't see the questions.
Yeah.
It doesn't scroll automatically. I think it's mouse.
Yeah.
I think we should. We can wait just a couple of minutes, and if anybody, because we still have the people there.
Sure. So I think officially, we'll stay on the line for any further questions. But apart from that, we thank you for your time.
And also, if there's any questions, sorry, Jason, about Mallett technology. I would cascade Mallett technology, by the way. And if any questions about Mallett and IQ3 Connect or Ocean Engineering for that matter, please contact us on our website, www.mallett.com, and let us know. We may assist you if need be in the consulting side, the software side. We'll be glad to. Thank you very much. We'll wait a few more minutes to see if any chat questions.
Yeah, we'll hang on the line, but again, we thank you. We'll officially
leave the
adjourn.
chat window.
Yeah.